Hello and welcome to this video on the different chemicals and elements that are used to create various color flames. This is something apparent in fireworks, fiery celestial bodies, and fires involving chemical stores. The effect of different chemicals, or more accurately the elements within, can be used to great effect and provides extremely useful insights. Blue, orange, and yellow flames are pretty common. But what about green or purple fire? The fact that the colours from blue through to orange are considered normal is simply a matter of exposure. We know that most carbon-based fire burns this way. But when you introduce other chemicals, things start to change. There are a range of tests that use the colour of a burning fire to identify the components of a given sample. The most common of these is unsurprisingly called a flame test. This is used to reveal which metals are present in a given sample. All elements burn at different temperatures and show different colors as they burn. Some are more unique than others, and some are more apparent than others. The test itself involves introducing a sample of the element or an unknown compound to a hot, non-luminous flame, and watching what color the flame turns into. The grossly oversimplified idea behind this is that as the atoms within your given sample evaporate, they are hot, and because they've both evaporated and are hot, they begin to emit light. This light is what we see in the flame color. It's why you only need a trace amount of any given ion or metal in a firework to create the diverse and interesting light shows that we see. To give some idea about what different elements do what. Boron will burn a bright green. Calcium burns yellow to orange. Copper turns a something blue to green color. The same sort of color you can see when copper oxidizes. Iron burns a strong golden yellow. Potassium burns red through to a light purple color. Lithium is one of the more obvious as it burns pink to light red. Magnesium is a hot white. Phosphorous burns a pale blue-greenish color. Lead burns a proper blue color. Antimony burns pale green. Selenium bright blue, or in the case of certain movies, giant globules of extraterrestrial life. Strontium is crimson, and zinc turns a blue-green to pale green color. These are just a sample of metals that are used. It gives you some idea of the diverse range of colors it can be created. You have not just the metals themselves, but metallic salts and mixtures that can have the same or even more complex effects. For example, if you were to take potassium chloride or potassium permanganate and burn it, it would turn a violet color. That coloration is interesting in and of itself, but these are also somewhat readily accessible chemicals. If you take Epsom salts, which are a form of magnesium sulfate, it would burn white. Copper chloride or copper sulfate will turn blue. Calcium is orange. These are chemicals that aren't exactly hard to get, as said, and so you can begin to explore just what happens. The caveat is that you need to have a fire that is originally not colored. And when we say not colored, we're referring to a blue flame. It's called a blue flame despite the nature of what it is. These household chemicals are going to work for a different reason to fireworks. Fireworks largely rely on elemental composites. These materials are made up of a salt and a metal. The salt doesn't react the same way the metal does, and so when the metal is heated, it provides color, but the remaining non-metallic component to the salt does not burn up. On top of this though, it's worth remembering that you can't mix metals hoping to get different colors. We've mentioned that you need to have a particular kind of flame, and that's a colorless flame. You can also achieve similar results by soaking sawdust in these particular salts, or something similar that would soak up the metals, allow it to dry so the water is no longer there, and then add these to a fire. You can't mix these mixtures though. Once you start mixing them, you're no longer going to get a multicolored flame, or even the color you're particularly after. What you're going to get is simply your regular orange flame. We mentioned at the start that the reason you're seeing these differences is all down to the way the metals exist, and the fact that they turn into light. Specifically, when you start burning elements in flame, they let off electrons. Electrons, as you might be more familiar with them, are electricity, and electricity is simply a particular form of energy. The energy is also being imparted to these electrons through the fact that you are heating them. This excites them, giving them a high energy state. As they pass from high energy to low energy or de-excitation, they begin to emit photons. Photons are a particular form of light, and there are different wavelengths. Within the visible spectrum of light, there are several particular colors that we are more familiar with. You may have heard the acronym of Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. These are the colors that we can see with the naked eye, and each of those colors is associated with a different wavelength that is going to be visible from photons in different ways. As each wavelength has a different color, and each element burns in a different color, we can automatically assume it's emitting different and very specific wavelengths of photons. It's also worth noting that generally the pH of your element or chemical is going to have an effect on the color. The lower the pH, the more vibrant the color you're going to get is. This is because the acid will react to the heat in a more pronounced way than a more alkali or basic chemical will. These colors will also be warmer, or at least feel warmer, in terms of the general description of them. You also can't go and simply throw these chemicals into any fire. Different elements are going to react at different temperatures, and this means the heat can play a role in the color that you are seeing. Certain chemical reactions and certain chemicals will only react at lower temperatures. This allows you to somewhat specifically select for the color that's coming out and which element is being excited. This means that you can have multiple chemicals burning in sequence as the temperature rises, which can change the color if it's all burnt off at each time. If you have an overlap, you'll note that the color changes back to orange. This is something that's used in astronomy terms. It's one way to know what sort of star in a faraway solar system is burning. Particularly if the example star has a high iron content, it will burn a very strong yellow color. If there's more hydrogen than metals, it's a whiter star as it's burning the hydrogen and it's burning it very hot. This gives some indication of what not only the star, but by extension, the solar system it's in is made up of. If you have a lot of metal in the star that's burning, there's a good chance that that solar system's planets have a high metal content as well. The more complex the formulation, the more it has than just a single metallic ion or salt, and so these things can produce more complex, vibrant, and interesting colors. In general, when we look at celestial bodies like a star, we're only going to be seeing the predominant color coming out, and that tells us something but not everything. More advanced technology can analyze this and begin to find out if there's something going on at a much smaller level than the human eye can discern. For the average person, being able to see fireworks in a single color and have multiple go off simultaneously is considered more than enough. Most people aren't after complex visual displays that go beyond shapes and patterns. That does not mean that this sort of knowledge doesn't have a place. As mentioned, it can be used in the flame test, which helps to identify otherwise unknown samples. With this, hopefully you understand a little bit about what different chemicals change colors in particular flames and why. As mentioned, there are more details and we'll have links to articles below that explain what other chemicals and elements can have the effects that you see. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions that you have below.